Hello YouTubers, Richard here. Welcome to episode 4 of my Engage Antics series of videos about using Arduinos for control of DCC accessories. In this episode we're going to be looking at the Arduino sketch running on our DCC Listener and understand how that works. I thought it might be worth just a couple of minutes on the Arduino IDE. It's really beyond the scope of what I'm planning to cover to explain in detail how to program an Arduino. There's lots of stuff out there on the web already, but I thought I'd just do a quick anatomy of an Arduino sketch. If you've done any sort of programming at all, this will hold no fears for you. Even if you haven't done any programming, don't be frightened, just roll your sleeves up and have a go. It's not nearly as difficult as it might look. So the Arduino IDE that we've got on the screen here is available to download for free from Arduino. It's an integrated development environment, which means that you've got the editor for creating your source code in a text editor, and you've also got automatically the ability to compile it, link it, and download it, or is that upload? Upload the sketch to the Arduino. The language that's used is C++. But personally, I believe it or not, I've never used C++, although it's very, very common. I have, however, used JavaScript, and syntactically it's very similar. So once you get your head around all these silly curly braces and so on, it's not difficult to work with at all. Now, every Arduino sketch pretty much has the same elements. We typically have the declarations at the top where we're including any external libraries and defining what sort of variables we're going to be using. We then, if we write any functions, they will appear next. So this is something that can be called from elsewhere within the code. Then there's a setup, which is a standard Arduino function that runs every time the device powers up. So if you're preparing anything, this is where you do it. And finally you've got the loop at the bottom, which just goes round and round and round as long as the device is powered up. I've written a very simple sketch. It's only one step removed from the hello world, but that does demonstrate the different elements. So in our declarations we've declared a single variable of type integer called counter. There. I've written a function which can be called from elsewhere, and all that's going to do, it's called my function. It takes a single parameter, an integer, which will be referred to as C, which is in the function header there, and what it's going to do is just print out to the serial monitor the value of C. In the setup code, this is the bit that runs when you power the Arduino up. We've established a serial monitor session, that's the serial begin, and we've initialized our single variable to the value of 0. So it will execute that, and then it will proceed immediately to the loop, and it will just keep going round and round, running that repeatedly. And all that does is add 1 to the value of our counter variable, and then calls the function, my function, which will print it out, and then it will delay for 1,000 microseconds, which is 1 second. So I'll upload that. So I'll open a serial monitor, and surprise, surprise, it's counting 1, 2, 3, 4, 5, 6, 7. Now I want to show you how to find the DCC monitor Arduino library by Minor Bay. If you type Minor Bay space DCC into Google, you'll find it straight away. It's the third hit here in GitHub. I'll click on that for you. And as it says, this is an Arduino library for creating NMRA DCC decoding devices. And there is the library. So you need to download and install that in your Arduino IDE. I've connected my USB cable to the Arduino Uno with the DCC shield, and this is the sketch that it's running. I'll just quickly upload the sketch so that the debugging becomes available. Whilst it's doing that, I'll just talk you through it. We're including the DCC_decoder.h DCC Monitor library, which is written by a guy called Kevin Snow, and is an outstanding piece of work. It works extremely well. As I said in an earlier episode, this is an example where you can use something that's technically quite complex without really understanding how it works at all. That's certainly me. Kevin's been very generous with his knowledge and made this available for free by anybody who wants to use it. The sketch that I'm using here is just listening for DCC accessory commands and then sending them out through the I2C network to the other Arduino, which is doing the heavy lifting. So I'll quickly talk you through what's in the sketch. We've got the includes, the DCC monitor stuff, wire for that network between Arduinos. We've got some simple variables, what the last command was, what the last address was, and an array of accessories. I'll show you what that's for in a moment. We've got the DCC KDCC interrupt definition, which I don't profess to understand. And then I've got a definition for debug so that I can turn debug messages on and off easily. We've got the packet handler subroutine, which is registered as a handler. We'll show you that registration down here in setup. We've got set accessory decoder packet handler here to be a function called basic ACK decoder packet handler. So if we go back and have a look at what that's doing, and it ain't much. The first thing it does is, and this is Kevin's code, not mine, it converts the packet into human readable form, and then I've checked to see if the command and address are the same as the last one, because we find that the command is repeated at least twice to make absolutely sure that the accessory hears it, so to speak, and we only want to action that command once, so we're trying to filter out duplicate commands there. So if we've established that it's not the same as the last command, the next thing we've got to do is make sure it's for an accessory address that we know of. So we check that its address is greater than 0 and smaller than the size of this list of accessories, which we've got loaded in an array, which tells this sketch which network address to forward the command onto. So if it's within our range, then we use the wire library to write first the address and then the command, and then we close down the transmission. And we're using the list of accessories and controller addresses to determine which address to send that command to, which is the final piece of the puzzle down here in the setup, where we say what address on the network we're transmitting the packet for any given accessory to. And finally we store the last command and the last address so that we can compare the next one with it to make sure it's not a duplicate. Now, as anybody who's used Arduinos knows, all these sketches have a loop function, the main loop, and all this one is doing is calling a DCC loop function in the DCC monitor library. What that does is see if any interrupts have been triggered and retrieves the information about the command. So what I'll do now is fire up the monitor, and I'll trigger a root, and you can see what it's done. Lots of duplicates in there because I seem to have it configured to send each one 4 times at the moment. That's something you can configure in JMRI. And for each of the 8 accessories that were triggered by that root, we've established that the Arduino controlling the servo for that accessory is on address 8, having first checked that it was a valid address. So the command was 1 for address 1 and 0, which means disable. So that was sent through the wire to the other Arduino, and it's done that 8 times. So a very, very simple sketch, but behind that a very, very complicated DCC monitor library. I'll close this. Now I would love to be able to claim that I've chosen this architecture with 2 Arduinos because it would enable me to have multiple controllers each running 16 servos, so I've got a sort of distributed architecture which is more scalable. In fact, it was nothing to do with that. I tried to do it all on one Arduino and found that I couldn't really get it to work reliably, and I've kind of worked out why. Kevin left a hint in his library code. If you look through it, it says make sure that you call this function regularly, by which he means every few milliseconds, or you will miss commands. And what is happening is that if you don't call this DCC loop function before another command is processed by that library, then the first command effectively gets overwritten by the second command, because when we call that function, what we're doing is going back and grabbing the information that has been stored temporarily by the triggering of an interrupt. I found that if you put any substantial amount of code in your sketch, then it simply can't call that DCC loop function sufficiently regularly to reliably get every command. So instead I've decided to have a dedicated Arduino which just listens to the DCC stuff and uses the wire I2C network to pass that command across to another Arduino which will actually process it. And I found that the interrupt triggered by the on-receive event of the wire library works very efficiently, so you never miss a command that's transmitted through that I2C network. But if you try and do it all on one, it just isn't going to work. It all looked great when I only had 3, but as soon as I thought, well, I better test the maximum number I think I'm going to come across, which is my 8, it was missing every other command basically. So this architecture works much better. So I'll try once again to summarize what this sketch is doing. We've got a loop function which just runs round and round and round and round, and that's every time it loops calls the DCC library to update any new commands that have been received. That's got a callback function configured in it, which is the function that we looked at, which transmits the command to the other Arduino. So when the loop function's called and another command's found, that function gets called and it gets transmitted to the Arduino that's got the servos attached to it. We keep a list of the DCC addresses and the associated Arduino with the servos on that the command needs to be sent to. Now, for performance reasons, I took the decision to use the first available 16 addresses. So I'm using DCC address 1 through 16 for these servos. That gives you performance advantage because you don't have to run through your list of configured accessories to find the one with the DCC address that you're looking for, because you already know that the first DCC address will be the first entry in the list and so on. So address 10 will be the 10th entry in the list. That's rather like using the primary index in database speak, but it's a sort of direct access technique which is much quicker than having to go looping through looking for the address each time. Performance is very much at a premium with Arduinos, so I think it's worthwhile taking that approach, but you can do it the other way if you want to. I've made these sketches available on GitHub. feel free to download them and have a closer look. That's the end of this episode. In the next episode, episode 5, I'll be having a look at the sketch running on the Arduino with the servo controller on for points control. I hope you found this interesting, and I hope you'll join me for the next episode. Bye.